now.
Okay, perfect. Hi, everyone. Assalamu alaikum. So we're going to show you around today the CMS experiment, and it's a great time to visit the CMS experiment because what is happening now is that we're not taking data, and you would think that this is not a good thing, but it's actually the best thing that can happen for visitors, even for virtual visitors, because that means that we can actually go in front of the experiment and we can show you what it looks like. And even more than that, these days, CMS is actually open. As you might be aware, that when we're taking data, all of the detector components, they're close together, and it's a very compact object. So that's why we call it CMS, right? So it's a compact muon solenoid, unlike some of the other detectors. Uh, but at the moment, what is happening is because we're in this so-called long shutdown, where what we're trying to do is make improvements to our detector, and we will stay in this position for 3 to 4 years. We are actually opening up, and we'll see today how we open the detector up. We're opening up pieces and slices, and we do it this way. And so it is the best time to have a visit, because then we can actually see what's inside of that. We have these slices, which we call discs, separate, and you can actually look at what's inside of those slices. So we'll do that today. Let's start with some introductions. So I'll start with Ahmed.
Assalamu alaikum. My name is Muhammad Ahmad. I'm a postdoc in Texas A&M University, working for CMS experiment. My main activity, I'm do data analysis, and I participate in one of the muon chamber, which is on the end cap of CMS, which Ansar will go down and try to show you around. In relation with Pakistan, I did my master's from Punjab University, Lahore. That was my last degree. So I'm working for CMS from last 14 years. What do you?
Yeah, you didn't say your PhD. Your master's was not your last degree.
From Pakistan.
From
It was
Pakistan,
my
it was
last
your
degree.
last degree, and then you did PhD. Okay, so I'm Ansar Iqbal. I'm also from Pakistan, as you can imagine. So I also did a master's. This was from Quaid-e-Azam University, and I did the research where you're sitting now in NCP. Then I came here, did the PhD from Germany, and I have been based here at CERN since then. At the moment, I'm a postdoc with UCLA. So yeah, and in terms of activities, they're also, as you will see, all of us that work with CMS, we're doing many things. So, for example, I am also working on analysis, and then with the same muon system, we call it cathode strip chambers, CSC. So we'll show you actually these chambers, and then some activities in communications and things like that. So, okay, so we'll move on.
Assalamu alaikum, everybody. I am Zainab Aamir, and I'm currently a summer student at CERN, and I'm doing my master's in robotics and artificial intelligence engineering from NUST. So I am here for about 3 months, and this program is for mostly for students who are either in their bachelor's or in their master's, and it's open to everybody, and especially like if as Pakistan is an associate member state, so the master's and bachelor students can apply for this.
Okay, great. So let's hear from you. A couple of things that we would like to mention. First of all, is that ask a lot of questions. I mean, you can ask questions at any time, and really, we mean any time. You can interrupt us and just say your question. You don't even need to, raise your hands or whatever. You can just ask us questions. And one of the things I say always is that we as scientists, it's our job to ask questions about the universe. And it is also our responsibility to encourage everyone to do the same. So there are no stupid questions. If you have any questions, if you see anything, for example, now in the background, we're sitting in the control room, you can go ahead and ask us questions at any point in time. So let's start with the introduction. I assume that you guys are familiar sort of with the LHC, as this is the LHC stool, and I.
For interrupting, in the meantime, I think you could.
I can do that, and you prepare to
Okay.
go.
Yeah.
So what we're going to do, just to explain to everyone, what we can do is that Ahmed will explain you the things, give you the primer, which you'll be aware of some of the things. And then in the meantime, I can try to prepare, because we're also going to take you down. So I can prepare. We have to do a bit of preparation for that. So I'll prepare to go down, and then we will switch to the other camera, and then you can also visit with me CMS. So okay, so I'll pass you to Ahmad, and he will give you the basic introduction.
Okay. So we are sharing this, right?
Yeah.
What you see here, the yellow tunnel, it's called Large Hadron Collider. It's a 27-kilometer tunnel, and then you see these white points. There are 4 experiments installed. So what we do in this tunnel, we accelerate proton up to roughly speed of light, and once they are moving with 13.60 V at center of mass energy, we collide them at 4 different points. So 4 different points you can see highlighted here: LS, Atlas, LHCb, and CMS. These are the 4 experiments installed on the tunnel. And today we are going to visit CMS. So Ansar will be going underground to CMS. It's a 100-meter deep experiment. So you will have because July last month we stopped for long shutdown, 3.5 year break. So we are not running anymore. So that's why there is a possibility to go down, and you can even see the detector itself in open state, which is quite fascinating. So there are other experiments also. If you try to see, like in terms of map, what you see, this dashed line, it's a border between Switzerland and France. So some area is on Swiss side, some on French side. At the moment where we are sitting in CMS is close to a French village called Cessy. What also you see on the background, this lake, Lake Geneva. And then you see the Swiss Alps on the background. Maybe some of them are French Alps as well, mixed. And then you see this sun main site. One is Mega here, and one is Prevesa. And then you see other also some smaller tunnel like SPS, which is about 7 kilometer. Then we have a linear accelerator here, which we start with to begin with, where protons are ejected. And then once they get enough energy, they go to bigger and bigger tunnels sequentially, and finally into Large Hadron Collider. So we'll switch to the other camera to show you how Ansar is getting in. So he's going to this area. Going underground is very restrictive. So you put your dosimeter in, you go inside the room, you scan your eyes to get access. And now one of the member from our technical team is going in with Ansar. Okay, we're walking towards the elevator, which will take them to 100-meter underground. So if you have anything to say before you going to the elevator, you can say now. Otherwise, I'll carry on.
Where is the mute button? Can you guys hear me?
Yes, very well.
Okay, perfect. So as Ahmad was saying, this is our elevator. We'll go down, and here actually you can see where the elevator is. So you can see it's pretty fast, and it goes down to 100 meters. It was already down there, and it's coming up now, and we will go down. So when you see, for example, in buildings, there's first floor, second floor. So the first floor is what, like a few meters, right? So the first floor, -1 that we have here, this is minus 88 meters. So as you can imagine, this is pretty down underground. So one of the things that I like to ask the visitors is, there are a few reasons why we have everything underground. So while we go down and we're exploring underground, I'd like all of you to think, what is the most important reason why we have built everything underground? I mean, you can imagine that this is quite a bit of a hassle. We have to take everything underground. We have to go through so many checks. Why not just build the LHC on the surface? There are a few reasons for that. There are a couple of scientific reasons, and then the most important reason, I would say, is not actually scientific. And so I like you to think about it. And then at the end, we can discuss again, right? So let's go down in the meanwhile.
Okay, so I'll take control for a couple of minutes because the connection is not very stable when you are in elevator. So let's move to next slide so that let's start projecting so that you know what we are talking about. So just showing you quickly the sun accelerator complex. You see the linear accelerator here where I'm pointing. That's where we start with. So we take the simplest element of our universe, which is hydrogen gas. It has only one proton, one electron. We ionize the gas and inject the proton in our linear accelerator and then apply electric field to accelerate them so that they move faster, applying electric field. Once they are fast enough, they go to bigger and bigger tunnels sequentially, which you can say they go to booster first, and then to PS, then to SPS, which is 7 kilometer, and then finally to this bigger ring, which is called Large Hadron Collider. What you see on this bigger ring, yellow points, and also see this arrow. So in the tunnel, you would have two proton beam, one clockwise and one anti-clockwise. We let these two proton beam cross each other at 4 different points where they collide, and then the experiment installed on these 4 points try to record everything what happens during collision. So we would be, as I said also earlier, that we would be visiting this CMS, and Ansar is underground. So I give
Okay,
over
so
to him.
if you can see us, now we're underground. There is 100 meters of earth above us, which is crazy. And now we're going to go in. So one of the things that we have to take care of is that when these collisions are happening, as you can imagine, there are protons colliding, smashing into each other at nearly the speed of light. There's a lot of radioactive material that's being produced at the center. So when these collisions are happening, of course, no one, and this means us also, we're not allowed inside at all. Even when the collisions stop, we have to make sure before going in that the radioactivity has cleared away, and then we can actually go in. And we take a lot of measures to ensure that. So for example, one of the things that we always do is carry this thing. This is a dosimeter. So it's a radiation dosimeter that everyone who works down here, they have a personal dosimeter, and they basically measure any radioactivity that we possibly receive, and then we take measurements regularly, and then we see how much radiation we've received just to be sure. Then what some of the things that we have also here is that in order to go in, you have to badge first your dosimeter so that it makes sure that you are actually allowed to go in. And then there's this James Bond scanner that Noemi is going to show you now. So it's an iris scanner. And so I'll scan my eyes and it will know that this is actually indeed me. And then we can go inside. So I'll show you. We do this again. And then it will open. So now I'm going to scan my eyes.
And so another thing which is checked in this, there is also a laser installed in the door, which makes sure that you are not carrying any material, and also it's a single person going inside. And you see now person from our technical team, they are scanning their retina, and then if it matches, the next door open, it's a double door.
Okay. So now we're almost there. Just to say that any walls that you see right here, for example, these are not ordinary walls. In some places, we have 8 meters of concrete just put in here, and there are very good reasons for that. One of them is just if we're colliding things down here and there's radioactive material here, we're able to still come here because all of this material that blocks some of the radiation. This is one reason. But there's another really interesting reason for that. And this is that when we were building this detector, so there is this thing which is really heavy called the compact muon solenoid, CMS. So you can imagine that this is a really heavy metal piece which is bigger than the Eiffel Tower. And then we want to put it inside of this cavern, and there's a plate underground. And so you put it here, but then in order to work, we've dug these spaces, so it kind of becomes like a bubble. So what is happening is that you put a weight here. So it wants to bend. And so what did we have to do? We have to actually put a counterweight here. So this is the concrete that is here so that it stays level. So let's go in.
Okay,
And here we go.
3, 2, 1, go. Okay, what you see is actually it's quite rare to see that you have a CMS detector and accessible and also in open state, which only happens during long shutdown.
So what you're seeing here, for example, is, as I was saying, we have built CMS in slices. So you have these disks. As you can see, for example, this is one disk. So it's one component of it. And we have a few disks. So you can see that these two disks we have opened up fully. So they are towards this side completely, to one side of the cavern. And then we have this space. Why? Because we want to do some works inside of this space. And then you see this disk. You can see how high it is. It's a few stories high, like a few stories high building. And then the things that you see on that, these are individual detectors. The detectors that we have in these disks towards the end, they are mostly muon detectors. And the numbers that you see are just naming these detectors, which individual component this is. If you move forward a little bit, this is one of the disks, and then you move forward, and then we come here. So this spectacular thing that you see, this is actually the meat of the detector, what we call the barrel region, which is in the middle. And we have opened it up, and you see what you see in the very center, this thin, narrow tube. This is the beam pipe. This is where the protons are actually coming in and then colliding at the center. So the collision point is actually more on that side. It's in the center of these layers that we're going to see. But this has been opened up, and what you see we call the nose of the detector. There are also subcomponents in there, some muon detecting chambers. And so yeah, this beam pipe is there. It's also going to be removed as part of the activities, and then we're going to make improvements basically to everything that you see. This is going to go out, and then we're going to make improvements to these things. Some of the components are going to be completely removed, and new components are put in. For example, we'll show you later, but one of the things that we are going to replace is just close to the nose of the detector, there's a detector which is called a calorimeter, and you can hear the word calories in there, right? So it has to do with measuring the energies of the different particles that are being produced in these collisions. So what we have now, this is different types of calorimeters. There's for those of you who know, there are electromagnetic calorimeter, hadron calorimeter, and they're basically detecting different types of particles. So what we're going to do now is make it much more granular, because at the end of the day, the more fine we can go, the more fine we can resolve these components, these particles that are coming out of a collision, the better physics we can do with that. And so what we're building now is called a high granularity calorimeter, HGCal. And we're also going to show you some of the components for that are being built. This is on the surface. And there also Pakistan has a role in that as well. So this is one end of the detector, and then if we move towards the core, so all of this that you see here is the center we call the barrel. And if you can imagine the CMS detector, it is just like a cylinder. So the discs that I was showing you earlier, they were the lids of that. You can imagine this is called the end caps. And then here, this is called the barrel. As you can imagine, if it is a cylinder, so the curved surface of the cylinder, this is exactly that. And you can imagine, you might have seen CMS in pictures, but it's really huge. And this is you can have an idea of the scale of this thing from the video that we're showing you. So if we move on, so maybe one interesting thing that we can show you is this is the surface of the cavern. But if you look down, there is also a few layers of floors under there, and these are called trenches. And so when we tell someone we're working at CMS and we're working in the trenches, we mean that really literally we're working in the trenches. And why are they here? Because, well, this whole thing, you will notice that there's lots and lots of cables everywhere. And these cables are for doing many things. You have to provide power to the detector. You have to read out what we're recording. You have to provide what we call triggering. Then you have to read out the data. Then you have control signals that are coming in to make sure that we can change, for example, the voltages or the operating points of detectors and so on and so forth. And then we can monitor things. We have cameras as well to know things. So there is going to be a million cables in there, and I'm not joking. There's millions and millions of cable down here. And so, yeah, so these trenches are things that are connecting this experimental cabin with another cabin that we have upstairs where all of this readout goes, and then you can distribute all of that data from there to the laboratories all over the world, to the universities, and then you do your data analysis from that. So if we move forward a little bit, so where we were just a few minutes ago, this was the plus side, according to our convention. And now where we are, this is the minus side. So it's kind of the reciprocal. And you can see, again, the barrel part of the detector, it ends here. And then on the other side, this is the end cap. And we have all these different detectors in this big disk that you see here. This we opened up first, just to say. And because it was opened up first, we are a little bit more advanced here in terms of what we're doing. So, for example, one of the things you notice here is that there's this big, huge platform on the top. So why do we have it here? Because, for example, if somebody wants to work on the detectors that are inside of this thing where the nose goes, how do you work? Well, this is kind of a problem, right? So we built this full structure so that people can actually go up. There's a scaffolding here that people can actually go up, and then you go up on this platform, and then you work inside, and you remove some of the components. Actually, you are removing most of the components because they're going to be thrown away, and there's going to be a new tracking detector that's installed there. So all of these activities, which we call decommissioning activities, are happening these days. Then one of the interesting things that you might see is that if you see here, there are detectors on this side, and this is the silver type thing that you see. But this structure, this big red structure, which makes most of CMS, this is actually solid iron or steel. And if you see here, you see this notice which says HMC3, Pakistan. So many parts of this what we call yoke, they were actually manufactured in Texila. And so that's a great thing. This is amazing. We can also show you if we go towards that side. Yeah, so if we there's one other interesting thing that we can show you, which is that there is still some magnetic field inside of this yoke, because CMS has a magnetic field when it's operating. And in order to demonstrate that, these are normal paper clips, but if I stick it here, this is still magnetic because yeah. And so when CMS is operating in particular, the magnetic field is so high that even if you're not here, you are meters and meters away outside this shielding concrete that I was talking about, you can still take these paper clips and even try to map the magnetic flow lines. You just hold it and it goes like this. So this is so strong. Just to give you an idea, the Earth has a magnetic field, as you know, because of which you see these beautiful northern lights and so on. The magnetic field that we have in CMS, this is 100,000 times stronger than that. So this is one of the strongest magnetic fields ever produced in anywhere. So an interesting thing that we can see here, if we move to the center of this space, is I want you to look up. So if you look up, there's something interesting. So go up, up, up. Uh-oh, you see a big hole in the ground. And this is actually going to the surface. So the yellow crane that you see at the very top, this is on the surface. So why do we have it here? Well, when we built CMS and even afterwards, how do you build such a thing? It's kind of like building a ship in a bottle. So what do? You have material and components coming in on the surface. You do some pre-assembly on the surface, but then you have to lower it here. You cannot use normal elevators and things like that to bring things here. So what you do is there's this big crane and you put things here, and then you take days lowering them down into this detector in this cavern, because I mean, these are thousands and thousands of tons of equipment. And so you have to do that very slowly, very carefully. And so just to give you an idea, for example, this blue structure that you see here, a few days ago, this was picked up and dropped here and dropped there and moved. All of this can easily be done with this huge crane, and that is amazing even to think of. Okay, and so if we go here, one of the things we might be able to see actually is very relevant for us. If we go to the very end, yeah, well, let's go up. So now we're going to go up, which is weird. We're in a cavern and we're talking about stories, and we have let's say 5 stories here. So it's a bit of a hike going up. So we go up, up, and one more. So first of all, let's check a different view. So if you look here, this is a different view, and here you actually see. So this is the equipment that the people working on this platform are working on, and you see here that now you don't see the beam pipe, which we saw earlier. Why? Because it has been removed. It was going to be removed, and it has been removed because we're also going to remove all of the other stuff here. So if you move here a little bit and look at this nose part, now you see that it's a little bit different from the other side because the material that was wrapped around here, that has been removed. And what we're doing is now we're starting to remove again, these are muon detectors inside of that. And we're starting to remove some of the components from these detectors. Okay, if we go this way, I think, the flag. Yeah, we can see from here. Okay, yeah. So what you see here is this is, of course, all on that side, and it has been moved to open up the detector. And here you see again something that you might recognize. Yeah. So here you see, yeah, because it's a circle, so so you see the flag of Pakistan, and then it says HMC3 Pakistan, because all of this structure again was made in Texila. So that's amazing. That's something to be really proud of, and something really inspiring. Okay. And then typically when you're talking about electronics equipment and scientific equipment, you think of it as something that sits on your table and is small. But here it's so big actually that you see that stairs are going actually on top of that. So there are these stairs, but there are also these stairs that go on top, and we can actually go there. We can't do it now because it's in a different configuration, but usually in the barrel we can do. So yeah, so this has been moved here, and we actually work on all of this stuff that's up here. So let's go there and actually, yeah. Well, it's okay. So we're going there, and in the meantime, maybe Ahmad can take any questions if you have.
We rely on the local organizer to.
Ahmad,
Ji.
there is one question.
Yeah, sure.
Hi, am I audible?
Yes, I can hear you.
Okay, I'd like to ask, how much time does it usually take to like collide two beams together? I'd imagine if they're traveling in the speed of light, so it just takes several seconds, but you can tell me better. And also after you're done like colliding two beams, and how much time after that are the like people allowed inside the collider?
Let me take the second part of the question first, and I admit I do not understand completely. What do you mean when we are colliding, people staying there? Can you tell me again what you want to ask?
Yeah, so
My question was when
the
we
first.
collide.
Go ahead.
My question was that when you're colliding beams in the collider together, so how much time does it usually take? For example, if two proton beams are colliding, how much time does it usually take them to collide together after they're sent into the collider? That's the first part of the question.
So, I mean, when protons are in the beam, they are in the form of bunches. So we let two beams cross each other, and the bunches collide, and the gap between two bunches is 25 nanosecond. So after every 25 nanosecond, there is one collision. If you convert this to a normal unit, that means 40 million collision in 1 second. And we are the beam are just keep crossing each other, and the collisions kept happening. So 40 million collision in 1 second once we are running.
Okay, and once the experiment is done, then how do you clear off all the radiation inside the collider? And how much time does it take? Is it like weeks or months?
No, it's not weeks and months, but I would kind of direct this question to Zoltan, like how exactly the radiation sweeping team generally delays.
So concerning the experiment is not just one collision. The experiment is something when we fill up the accelerator, we can run it for several hours, making proton-proton bunch collisions 40 million times per second. And once the beam is depleted, we drop the beam, and then either we refill or we have a possibility to go in for something very urgent maintenance. This, I think, I understand your question as how much time after the beam turned off to go in. It's something like half an hour. The reason is less radiation, but rather other safety. The radiation immediately decays to the level that we could go in, but we have to change the the air circulation for a faster air replacement, and also we have to wait until the voltage in the dipole magnets in the accelerator goes down. Otherwise, if a quench happens and the helium is released, then it would be a problem. So we decrease the safety issues. So it's not radiation.
So in summary, like 30 minutes. After we stop colliding, people wait for 30 minutes before going in.
But then this is just the so-called interference. In every 6 to 10 weeks, we have a few days of technical stops when we get something like 2 to 3 days to go in to make something that some maintenances that are not extremely urgent but urgent enough to be made. At the end of each year, we stop for the Christmas time here, something like
December
2-3
to
months.
February.
Something like 2-3 months. This we call as a year-end technical stop. Then we can make bigger, slightly bigger maintenances. And the situation where we are now are the long shutdowns that follow each other, something like every 5 years-ish.
Yeah, and we close for a few years.
Exactly, and now we are doing major changes to the detector, to the accelerator. Thank you.
Yeah, a few things to add, just because. So one of the things is absolutely. So the radiation goes away, and why is that? If you think about it, the collisions are happening at the very center of CMS, right? And so there is this huge amount of material outside, and that's the whole purpose of this material, to stop these particles, right? Because if there is a collision, there's going to be hundreds of particles that are coming out. And the whole point of putting all of this material outside of that is to stop that. And generally, when we're colliding, all of this is closed. And so there is no radiation there's not that much radiation that really leaks outside of that after a certain amount of time. And this is the reason, if you think about it, what we're doing is we're colliding the smallest particles in the universe. We're trying to look for the smallest particles in the universe. So the first question that comes to mind is, why is this thing so huge, right? And so that's the idea. There are 2 or 3 reasons for that. But one of the reasons is that in order to really fully capture the energy and fully stop all the particles, you just need a lot of material, and this is a lot of material, and that's why it is so big. There's also that when the way you measure, the way you identify particles is by using a very basic physics principle, which is that you apply a magnetic field to any particle that is traveling. And what happens? We all know this. When you apply a magnetic field to a traveling charged particle, it bends. And the bending, it depends on a few things. If you have a certain amount of magnetic field, the bending will actually depend on the momentum. So if you know everything else in this equation, you can calculate what the momentum of the particle is. Now, if you have a large amount of space, you can do this better because then you can measure, okay, how much it bent over this much space. And so this is also one of the reasons why we have these detectors so big. A couple of other things to add to your first questions. So absolutely, yes. So we are, yeah. So what we're showing now is a illustration of what happens in CMS. So you apply this magnetic field, and then the particle bends. Interestingly, one way first, and then the other. You should be able to tell, or this is your homework to figure out why. So it bends one way in one place, and then the other way in the other. Why? So this is your homework. And then the other thing that I wanted to say regarding your first question was, yes, absolutely, we're colliding 40 million times a second. But in terms of what you mentioned, how much does it take, for example, for the protons to go around? The speed of light, we say speed of light is fast, right? So if I come, for example, from the main sun site, it takes me half an hour, something like that, to get here. But the protons are so fast that they're going around this ring 11,000 times per second. 11,000 times per second. So that's fast. And this is how much it takes for protons to go around this ring at 27 kilometers, 11,000 times per second. This is how fast it is. Okay, so now if we can switch to this camera, we're in another special place inside the cavern. Every place is really special. But now we're actually at the top of CMS. So this is the view from the top because we're open and we're standing on the barrel, the rings of the barrel. And now we're looking into the discs of the end cap. And as you see, this is the yellow platform that we were looking at from below, and you can see the ground also. So this is kind of like 5-6 stories high building, and we're at the top. And if we turn around, for example, you can see how CMS looks like from the top. So this is it. You see these cranes that are used for all these operations, and that really is the top of the cavern. You see the curvature at the top, and then there is again this shaft that we use, big shaft that we use to bring in material, take out material, and things like that. So yeah, pretty impressive, I would say. Okay. Let's start heading back, and in the meantime, if there are any more
yes,
questions, we can.
Answer. Here is
Yes.
a question.
Okay, so my question isn't really related to CMS experiment. It's rather about, is there any work going on in CERN that is related to quantum information sciences? So
Yes.
recently I read about Lickens lectures and they were related to quantum information sciences for particle physicists. So I just wanted to know that.
Yeah, I mean, there's many things. First of all, what I wanted to say, but then other things came up, was Zoltan mentioned and also Ahmad mentioned that we're doing this lots of collisions, right? Why? Why do we need to do lots of collisions? For example, if we say we want to discover a new particle, we collide things together and we see a new particle and that's it, right? Right? But that's not how it works, because everything that we do is at the quantum level. So what is happening is all determined by quantum mechanics, first of all. So we have to do lots and lots and lots of collisions. We have to take data for many years. For example, we're still coming up with results with data that we collected 10 years ago, 15 years ago, things like that. So first of all, quantum mechanics is really important for us to understand, to implement, to use. So that's one thing. But regarding your question about quantum information, absolutely, there's many things going on in at CERN, which I can send you some links to. But for example, I can mention one thing, which is really cutting edge, and So what are the two kind of most recent things that are happening in the world of technology? One is quantum information, of course, but then there's also machine learning, right? Everything is now AI and machine learning. So I always thought of them as really different things. There's machine learning, and then there's quantum mechanics. But one thing that is happening, and CERN is at the forefront of that, is that we're trying to combine these two. So there's something which is called quantum machine learning that's going on. And if you think about it, it kind of makes a lot of sense, because what we do is we use machine learning in all of these algorithms that help us identify what's happening in these collisions. So we're trying to analyze, for example, what we call jets, which is just a spray of particles that comes out. Now, we have been making algorithms and using them for decades, but these are like your classical algorithms. But one of the things that has happened recently is that we have started using machine learning, and especially quantum machine learning, to have algorithms that are actually good at doing this. And we have demonstrated that this can go a long way, really. So this is just one example of how quantum information is being implemented at CERN, at CMS, and in other places. Okay, so what we're going to do is we'll start heading back up. And in the meantime, because we're going to lose connection, you guys can talk to our colleagues at the surface. So we'll meet you at the surface, and then we show you one other thing.
Okay.
Yeah, we can continue if there are
With
other
the
questions.
question.
Yeah,
Here
yeah.
is a question.
Hello. My question is not very technical, but I always assumed that since the collisions are happening inside a vacuum, it would be very silent when the CMS is running. But in one of the recent lectures at the school, I think it was Dr. Miller who mentioned that when it is running, there is this interesting sound that can be heard. So I was wondering, I guess that's the sound of the actual machinery that's being used instead of the collisions. And how loud is it? Like, can you feel the vibrations in your control room, or can it be felt on the surface, or is it just very dim?
Okay.
So it's pretty loud, but it's not physics.
Yeah.
I mean, the collisions don't have any sound. Collisions, as you mentioned, they take place first of all in vacuum, and also these particle collisions don't have any sound, any noise they make. On the other hand, there is a sizable noise that will anyway be bigger after LS3, but this is the noise of the cooling system of the racks. We have something like 400 racks downstairs. Each of them has some kind of cooling. Sometimes turbines that are just rotating the air inside, and that's quite loud.
Yeah.
In the backend systems, we are also about to install a new type of backends, these ATCA crates, and they are famous not only for being very fast, but also very loud.
Being heavy as well.
Exactly, and very heavy as well.
And yeah, but in summary, I mean, there's loud, but on the surface, no significant
on the surface,
vibration or noise. It's 100-meter underground, and it's
That is absolutely correct. Let me add something here. What you guys said is absolutely correct, and this is the correct, right scientific answer. But there's something very poetic that happens. There is, in some collisions, especially when we collide heavy ions together, what happens, let's wait here for a minute. So what happens is that when we collide heavy ions together, for example, we collide lead nuclei together, there's a medium that's produced that's called a quark-gluon plasma. And so this medium is what we think the universe was at the very instant after the Big Bang. And so in that medium, what happens is that this medium actually becomes a medium for propagation of sound, for example. It's not sound that you can hear, but we have a result, for example, that came out last year, where we're trying to measure the speed of sound in this heavy ion quark-gluon plasma. And that's amazing. I mean, even that you can try to do things like that, that in itself is like nothing short of crazy. So in a metaphorical sense, it is very loud, yes. But as Zoltan and Ahmad said, that you cannot hear that sound. So it's that. Okay, we'll go up to the surface.
More questions?
Yeah.
Hello. I have a question. I wanted to ask about the radiation. So you said that it's quite radioactive inside when it's running. So as if I'm not wrong, the CMS detector absorbs almost everything except the neutrinos. And I don't think neutrinos are radioactive or harmful for humans. So from where the radiations are coming? Are those the particles that are coming out of the beam pipes, or is it something else?
So there are two parts. I mean, it's a very radioactive when you are colliding. So the area around beam pipe is very radioactive. But as Ansar said, that the CMS detector absorb most of it, but don't expect all of it. There is a gap also close to very beam pipe. That's
And-
one thing.
And also the beam itself brings in some stray radiation. Also due to the beam focusing, you get a radiation. In general, the detector cavern is filled up some gamma field and some neutron gas as well. And this is that activates up the detector. Our detector is mainly from iron. You saw it, something like 7,000 tons of iron. In the iron, due to the iron manufacturing needs, there are two materials that can be activated. The iron itself is not, but there is cobalt in it. The cobalt content can be decreased a bit, and we prefer to buy iron with less cobalt than the normal. But the manganese is something that you cannot decrease. This is an essential part of the iron manufacturing. And these two elements, the cobalt and the manganese, activates up. The aluminium also activates up a little bit that we see. And of course, in the electronics, we might get silver 110M, for example, as the leading radiation source. But in the integrated circuits, you have the full periodic system anyway.
Thank you.
But something I want to emphasize, this radiation level we are talking about, even if we say high, this is very low. This might be higher than the legal limit, and this is in some cases. That's why we have to be so strict. But we are very, very far from a nuclear power plant.
They're as compared to them.
I had a question regarding the radiation and how you manage with the equipment, because there's enormous amounts of radiation given off, and all of that is being absorbed by the equipment. So does that not damage the equipment or technology and all of the machinery being used in some way?
It does, and it was known when we built this machine. So everything is designed to have some radiation hardness. The closer to you are on the beam pipe, the more radiation equipment absorb. And they are designed to be radiation hard and with some expectancy of lifetime. We call this
some of the equipment we replace quite regular, like the Pixel. Now after the 25 years or something like 20 years, almost 20 years of the building, the tracker is going to be replaced. But yes, the detector parts are due to be radiation damaged.
And I mean, then there is an expectancy lifetime, given that a certain radiation dose, how much your material would last, and it's can be calculated.
When you select a material to be installed in the detector, we always require the material to be checked or certified against the expected radiation level on that very specific place where we install.
We call this aging study. So people put material in a radiation environment and study how it degrades with the amount of radiation dose and with time. So you know how exactly like how it would degrade with time. And then there is a life expectancy of every material. That's why we are replacing most of the tracker also.
Like you mentioned, in every collision, there are hundreds of particles being generated. Is there any way to accumulate any kind of particles
or they are all just vanishes?
I mean, more than 100 for sure. So what we
Yeah.
do, I mean, when you collide, you produce many particles. Some of them are unstable. They get produced and they decay immediately to their daughter particle. Some of them are stable. So for example, if you count stable particle, they are not a lot, like electron. And what we call stable in our CMS collisions means whatever exit from our beam pipe, which is roughly 3 to 4 centimeter, and enters in our detector, which is directly recorded by our detector, is what we can say like a stable particle. So all the unstable would decay immediately, like Higgs boson, WZ bosons, they decay, and then you only see their yeah. So they decay in the beam pipe, and then you only see their daughter particle recorded in the detector. While the stable particle, we do record E plus, E minus, we record jets, which are proton, neutrons, kaons.
Due to the hadronization of the quarks.
Yeah, and then we see muons in the outer ring, and then neutrino, which escape our detector. Everything.
Can you use these particles which are, stable, as you just say? Can you use these particles for another kind of experiments in LHC?
They are not being used. I mean, electron, positron, no.
We absorb that, actually. The calorimeter absorbs most of these particles because we have to measure their energy.
Yeah, only some muons and neutrinos.
Yeah, but they fly away. You can't even catch them, so there is no chance to reuse them.
And also they scattered in like every direction.
Exactly.
They are not a focused beam which you would divert to something.
So they are the signals basically which the detector is collecting.
Yes, a couple of things to add to that. Absolutely, what my colleagues are saying is correct. But there are some interesting instances in LHC. For example, one of the things that happens is that in particular, when lead nuclei are passing close to each other, or even protons are passing close to each other, one of the things that can interestingly happen is that they don't smash in the typical sense, but they pass close to each other, and then each of them emits a photon, for example, particles of light. And this is something that we detect ordinarily in CMS using our calorimeters. But what can also happen is that these photons, they come in and they interact with each other. And then there are particles that are produced because of that interaction. So what we also say in these types of particular results, this happens very rarely, but what we also say in these types of results is that we can use the LHC as a photon collider. So it's not only a hadron collider, but the LHC can also act as a photon collider. Not only this, but there's an even rarer possibility, which is that these protons passed away, they gave photons, and these photons are coming in, but a photon is a particle which is electrically neutral. It can decay into an electron positron, right? So it can do this pair production. So you do this electron positron, and then you have these two leptons that are going. And then the other one does the same. And then what you have is two electrons that are coming in the LHC, where there's no electrons anywhere. We use protons, right? But now you have these two electrons that are coming in, and they collide off each other, and then they can do this interaction. So we also say that very rarely, and this is a result that we produced very recently. It was just last month. We said that we actually observed that there are these electrons in the Large Hadron Collider that are coming out from the photons, which are out from the protons, and they are actually scattering off each other. So we also said that now we've confirmed that the LHC can also be used as a lepton collider, as an electron collider, for example, as a muon collider, which is the first ever observation of this scattering of muons with each other. So that's absolutely. So typically we don't do that, but there are interesting cases where we're actually using these particles for other collisions. It happens automatically. We're not doing anything special, but it happens automatically. So one final thing that we wanted to show you is now we're on the surface, and if you come here, this is the shaft, the hole that we were showing you again and again from 100 meters underground, and this is how it looks on the surface. This is actually opened up. What we can do is actually cover it up when we're taking data, when the detector is closed. We can close all of the space, and then you can actually even walk on this. But now, because we need it, we've opened it up, and this is the shaft that goes 100 meters underground. But then the other interesting thing in this area that we wanted to show is here. So if you look at this thing, so you remember we were showing you that there is this nose of the detector that has all these components in. Well, here is the next generation of it. So what this is what we talked about earlier. It's called the high granularity calorimeter. And the idea is that if you can resolve these particles that are coming out of the collisions much more finely, you are able to do much more accurate physics with that. And that is the whole point of this detector. So this will replace the current end cap calorimeter. And then what we're going to do is install this new high granularity calorimeter, and we will have much more precise measurements, which is good for two reasons. Because one, you get accurate results, first of all, and you can confirm that our theories are correct. But also, if you have a really accurate result, what you can do is say that, yeah, the observation doesn't actually fit my theory. And you can do this much better if you have an accurate result than a really ambiguous one. And so this will help us in what we call precision measurements and also searches for new physics, as we call it. And the thing that I wanted to particularly mention here was that this has many components in there. And one of the components, which is called absorber plates, is actually being made in Pakistan. It was partly made in Pakistan, and then there were people also coming over here, and then they're helping in the assembly. And so Pakistan has a big role in this project, which is the high granularity calorimeter. One interesting thing, which is a side note, which I found really interesting over the past few months, was that some parts of this detector, they have to operate at really cold temperatures. And so you have to cool it down. But in order to cool it down, you have to heat it up. What? So yeah, so the point is that there is parts that need to operate at really cold temperatures. But then if there's something really cold, there's moisture in the atmosphere, and that can condense on top of the surface of that. And so that is water, and you never want water in your running electronics. So what you have to do is inside there, you want a really cold temperature, but then outside of that, you have to heat it up because you don't want cold temperature on the surface. And so these things are really interesting. In order to solve one problem, it creates another one, and then you have to solve that as well. And so it needs a really good insulation. It needs heating and cooling at the same time, which is very interesting. Okay, so we'll come back to the control room, and in the meanwhile, you can
take the questions, right?
Yeah, absolutely.
Hi. You said that the particles travel at very close to the speed of light. So I wanted to ask, what effect does time dilation and length contraction have on those particles? I know that the circumference would be much smaller for the particles. But apart from that, what kind of effect does it have?
So these particles, what we send around the LHC are protons. The protons are stable particles, therefore, the time dilation that you mentioned, they don't feel, if they feel anything at all. But if you consider that it would be so nice to send around muons as well, we are not able to do that, but also there are some investigations for the muon accelerators in the US, of course, and they would, in this case, the time dilation really would do a role. In that case, as the muons are not stable particles, they decay in something like 2.2 microseconds. Their extended lifetime due to their speed would really do a change in the technology for the acceleration. I just calculated a couple of weeks ago that a 10 tera electron volt energy muon would live for something like 200 milliseconds.
Yeah, it's a long time.
Which is a long time. So according to your question, or if we would use particles that are not stable, yes, really, this would really count. In our case, for the protons, it doesn't, because the protons are stable particles.
That's absolutely true. So one final thing that I want to do is go back to the question that we were considering earlier when we were going down. Remember, I asked you a question, right? So why have we built all of this underground? So I actually would like responses. If there are any responses from the students, anyone would like to answer that? Because this is something that most people don't get really.
No, they don't speak.
Ah.
I guess.
My guess is that you mentioned a lot of radiation, so it being very deep underground would help with containing that. And also, since it's built in the countryside, I mean, I don't think you'd want to go around buying that much land and then making
Well, what did you say? The last one, the last thing.
Buying that much land in the countryside, specifically like
That's absolutely correct. So okay, there are a few reasons. One, there are a couple of mundane scientific reasons. Yes, you want to protect your detectors from the noise of the cosmic rays and things like that. And there is things on the surface which is vibrations, and so it's more stable. But these are like mundane scientific reasons. The real reason is money. It's always money, and so that's absolutely correct. So if you imagine there's this 27-kilometer ring, and if you built it on the surface, you have to buy the land. Not only in the countryside, anywhere in the cities is even more expensive. So you have to buy all of this land. But there is this rule in the host states that if you own a piece of land, you only own it until a certain depth, and below that, this is the government's land. It can do anything with that. So 100 meters underground, you don't have to buy the land. So this is absolutely correct. It's a money problem. It's not a scientific problem.
That is another country where the land is cheap,
right?
And they build the accelerators on the surface. That's the United States, where at the Fermilab, the Tevatron was built on the surface.
That is true. Okay, great. So I think we're running out of time.
They will tell, not you.
Well, we have to get back to work. But okay, if there are any urgent questions, please go ahead.
So, okay, if one last question, maybe, Ansar, if you allow me.
Please go ahead.
Okay.
You mentioned that you have to cool the, the nose or absorber, whatever that is. And also, when LHC is running, you have to cool the magnets. So what kind of material you use, water or helium?
So this is okay.
Costly? I mean, it's a lot of water if you have to cool the magnets.
So this is okay. There are a few things here. Good question. So there are a few things here. First of all, just to emphasize your point, we say that the LHC is simultaneously the coldest place in the universe and the hottest. This is again very surprising. Why? Because, okay, first of all, you have to cool things down, as you said. And why do we actually have to cool things down? Because these magnets that we're trying to utilize, they have to be superconducting magnets, because otherwise we cannot make these strong magnets. And in order to get to this state of superconductivity, we have to cool things down. And so we go to temperatures that are colder than outer space. So we said the LHC is one of the coldest places in the universe. But then also, if you consider when the collisions are happening, the energies in the collisions are so high that the average kinetic energy of the particles, the few particles that are there, is so high that the average kinetic energy, in other words, temperature, is one of the hottest temperatures in the universe. So it is simultaneously the coldest places in the universe and the hottest places in the universe.
And between them, instead of having billions of light years, you have sometimes 50 meters.
That is true. And also, so it's also the vacuum inside of the LHC is also rarer than outer space. So if you go to outer space, like there's nothing around, you have more particles per cubic meter than we have in the beam pipe of the LHC. So that's amazing. That puts things into perspective. And there's a joke that we have that the LHC is so cold that this is the biggest refrigerator in the world. This is the biggest fridge in the world.
Don't forget that the helium that we use for the cooling of the magnets in the LHC is 1.9 Kelvin. It's not the 4.2. It is superfluid. We use the superfluidity of the helium because then it can really penetrate everywhere in the magnet.
Yeah, absolutely. So it's not water cooled. It can never be water cooled. So we use
but we would need to use the water amount of Lake Geneva, which is one of the biggest lake in Europe.
Right. So we use liquid helium. Absolutely. And yeah.
So I think we are running out of time, and you also. So maybe if you want a few minutes, or we don't know, but if you can finish the tour at this moment right now, if you agree, it's okay.
Yes, we
Or
can
you have to
finish.
say.
But you can have a last question.
You can have a last question. Absolutely, we love questions, as you can figure out. Yeah.
Okay. So is there any question? I think yes.
First of all, I would like to thank you for giving such an informative virtual tour. My question is that what are the important operations that are performed in the control room of the where you are sitting?
Good question. So this is, I like to give an example of the LHC or one of the experiments. This is kind of like running your car. So what happens? You run your car regularly, you run it every day, but then after every 2 weeks, 3 weeks, sometime there is some breakdown. There's a tire puncture, something like that. So you go to the mechanic for a few hours, it gets it running again, and then you go on your way. But then once every year you do this big service. So you do all sorts of things. You might install some upgrades, things like that. So the operation of the LHC is very similar to that. What we do is we run 24/7 because we want to record all of the data that we can. Time is money for us because, as we talked about earlier, we want to collect as much collisions as possible. Then after every, let's say, few months, weeks, there is some 1 day stop, something like that. We call them technical stops. Then at the end of each year, I think Zoltan was mentioning this earlier, we have this year-end technical stop, which is a couple of months, which is the best time generally to visit CMS because then you can see the detector. And then after every few years, 4 or 5 years, we have this long stop for 4 or 5 years because then we actually want to upgrade things. Because you have to realize that what we're using is not we go to some shop and buy these components and put them in. This is something that's specifically made. This is something that we have developed for this purpose. And in a few years, there are more advancements that we can use, and there's more technology that we can use. And so we also upgrade these things. So this is the general cycle of operations. Now, coming to a question of when the operations are happening, we're sitting in the control room. So what types of things do people do here? The first thing which we take very seriously in all of operations is safety. And safety means many things. First and foremost is safety of the personnel that are working here. So, for example, one of the things we have to absolutely at all points make sure is that there's no one in the cavern when the cavern is closed for data taking. So that we make sure that happens. Uh, then the safety of the equipment and things like that. So there are people here who are looking at the safety aspects of it. Then there's one person who's sitting here who's called, you don't see them here because at the moment we're not taking data. But generally when we're taking data, there's a person here who's called the shift leader. And so just to say, these are not particular people whose job it is to do this. This is all of us. So we take shifts. So we take 8 hours shifts. A person can be a shift leader, and then after these 8 hours, the full crew will go away, and then there's another crew that replaces them, and this happens 24 hours. So there's 3 cycles every day when we're taking data. So there's this person called shift leader, and they are responsible in those 8 hours for the operation of CMS, for communicating with what's happening on the LHC side, because they are the one who are sending the beam. They are responsible for the safety. They're responsible for if the data that we're collecting makes sense. And we have a special person also for that who is making sure that what we're collecting is not garbage. I mean, it has to make sense, right? So there's these data quality monitoring people and things like that. So there's more expert roles over here. This is the central people who are from the CMS side. But then, as you can imagine, we have these different subsystems. There is this tracking detectors, I should say. Then there are these calorimeters. We have the muon detectors. And all of these individual subsystems, they have their own experts. And so there are people from each of the subsystem typically sitting in the control room or 24/7 connected and online and ready to act if anything goes wrong. So these are called shifters. So when data taking is happening, there's an interplay between all of these people, and they're communicating to make sure that everything is going smoothly, safely, and according to plan.
Okay, I think now we end this session. It's okay.
For us, it's okay.
So, yeah, okay. So thank you very much, Ansar, Ahmad, Zoltan, Noemi, and I forgot the name, the student.
Zainab.
So thank you very much from us that for your time, and you explained really fantastic, and we really enjoyed the tour of. And still there is the hand up for one question, and there he's requesting me to.
Okay.
Yep.
So usually, which are the busy days? The data acquisition days or the days when you are
It depends. Every day is busy day. It depends. When they when data is happening, it's a different perspective on things. It's a different type of busyness. Let's say we don't actually physically go in the cavern, but there's a lot of activity happening here, and people online and trying to analyze the data and look if the data is okay and trying to make sure that everything is fine. Now it's a different type of activity. There's not as many people in the control room as there are during data taking days, more or less. But now, if you go down in the cavern, this is full of people, full of all sorts of people. There's physicists, engineers, technicians, safety experts. We have radiation experts. We have all sorts of people working here. So it's always busy. That's absolutely right. But the nature of this busyness, it depends on what is actually happening at that time.
So finally, thank you very much, Ansar, for your nice time and your team from NCP Islamabad. So it's really fantastic. We really learn deep inside when you go there underground, and it looks that we were also there, not in Pakistan. So it was really, really very good and fantastic tour for us and very informative. Thank you very much for your time and your time of your colleagues as well. Thank you very much.
Thank you very much. Thank you.
Have a nice day.
Bye bye.
Bye bye.